Welcome to BuildUP, the European Commission's portal for energy efficiency and renewable energy in buildings. Directly stemming from the Energy Performance of Buildings Directive, BuildUP is the meeting place for everyone involved in making the European building and construction sector more energy efficient. Every month we focus on a topic that is key to making Europe's buildings as energy efficient as possible. Exploring that, you can find the latest content such as expert talks, webinars, case studies and more. From architects and engineers to academics and policy makers, we've got you covered. BuildUP brings together thousands of registered members to reap the benefit of Europe's collective intelligence on all aspects of energy efficiency and renewable energy in buildings. The BuildUP portal benefits from the expertise of our ambassadors. Drawn from industry and academia, the ambassadors bridge the gap between EU and national level and help shape our editorial content. Want to promote your work? BuildUP disseminates your research, projects and events through a variety of channels. Become a member to exchange knowledge with your peers. You can disseminate tools and resources, share good practices, and consult open source publications. Join the discussion on social media and become part of the BuildUP community, or subscribe to our newsletter to receive the latest news. However you participate, the BuildUP portal is here to inspire, inform and connect. BuildUP, the European portal for energy efficiency and renewable energy in buildings. Join the community for opportunities and updates.
Good morning and welcome to today's webinar. My name is Aranza Zugalan González and I'm a member of the BuildUP editorial team. It is a pleasure for BuildUP to host today's webinar and workshop event entitled Smart Energy Transition from Ideal to Reality, organized by the Welsh School of Architecture and the School of Geography and Planning of the Cardiff University, the Frederick University and BuildUP. Today's webinar is split into three main parts, and it will provide a hands-on perspective to understand what Smart Readiness Indicators, SRIs, are and how we can upscale their implementation considering the political, legal, and economic factors involved in translating practices from one context to another. Before we begin, we invite and encourage the audience to send us their questions or comments to the speakers throughout the session. To do so, please use the GoToWebinar question function. These questions or comments will be addressed at the end of the panels. The agenda for today's webinar is composed of the following sessions. Professor Paris Fokaides will set the stage talking about Smart Readiness Indicators for Energy Transition, an overview of the ideal. Johan Patterson and Emmanuel Perisiglu, professor and lecturer of Cardiff University, respectively, will talk about digitalized energy transition in Wales, reality check through a retrofit example. Anna Badina and Clarice Blale de Souza, research associate and professor at Cardiff University, will present the knowledge representation for comparing use cases in SRI implementation. At the end, we will have some time for Q&A session where Oleg Golub-Cheikov will join us and will be moderated by BuildUP. And now, without further hesitation, we will move directly to the first session. Paris, if you're ready, the floor is yours.
Yes, good morning, everyone. I don't know if you can hear me.
We do.
Can you hear me?
Yes,
okay,
perfect.
Great. So I would like to welcome you all to the introductory lecture of today's seminar. I would like to thank BuildUP and our friends at Cardiff University for initiating this very interesting seminar. In my 10 minutes presentation, I will introduce the Smart Readiness Indicators. I will discuss a bit about the concept. I will try to explain what the concept is about. And I will introduce the main aspects of the Smart Readiness Indicator as a new and novel approach for assessing the smartness of buildings across Europe. Now, what is a Smart Readiness Indicator? The Smart Readiness Indicator is a new scheme for assessing the smartness of buildings. And it has been introduced officially since 2018 through the directive for the energy performance of buildings. And the main purpose of the SRI is to introduce a scheme that will assess the smartness of buildings in the sense that it will allow the building users, to have a good understanding of how their buildings perform in terms of smartness. And of course, this will advantage the integration of smart technologies in buildings with the main purpose of reducing the energy consumption of buildings. So the smartness indicator is indeed a tool that is related to the energy efficiency of buildings. Why? Because we do aim to reduce the energy consumption of buildings through the upgrade of their smartness, and that is why we do consider that this is a tool that will also enhance the energy performance of buildings across Europe. Now, as you can see in the slide, as introduced, SRI was firstly introduced in 2018 through the EPBD, and it includes different aspects such as monitoring and reporting. The SRI is actually a catalog, a list in which we document the assets of a building in terms of automation and control. And through these assets, we are able to define the smartness indicator of the building. And of course, it's a scheme that requires the inclusion and let's say the contribution of different actors, including the scientific community, including the building physics community, the assessors that perform the assessments, the member states that introduce and integrate the scheme in their legislation, as well as other aspects that will be discussed in the next slides. So the main idea of the Smart Readiness Indicator is that it is based on three pillars. The first one is the one that we already have referred to, that is the energy efficiency of buildings. The second one is related to the enhancement of the comfort conditions for the building users, in the sense that improving the automation and control systems of a building, this provides a better experience for the users of the building. And the third aspect, the third pillar on which the SRI is built, has to do with the integration of smart buildings into smart grids, which is a major challenge that the SRI aims to support. And of course, the latter aspect, integration with the grid, is a crucial aspect, which has been observed to be, let's say, the weak part of our buildings today, in the sense that those indicators that we have introduced in the scheme for assessing the ability of buildings to interact with the grid appear to be the weakest, and thus the trends that are currently defined by the different components of the SRI is that the grid interaction is actually the weakest part. And apparently, we also have other components which are very important for the SRI. As referred earlier, the adaptability to the user needs. The SRI is a scheme that aims to enhance the comfort of the building users, and thus it is addressed to that. And of course, promoting automation and control systems raises issues of interoperability, which are also aspects that are handled by the SRI. Now, the assessment procedure for the SRI, we do have, let's say, the collection of the data that is related to the automation and control systems of the building. We do have our criteria for evaluating each, let's say, asset of the building with regard to its automation and control. And we do have tools that are used towards calculating the smart readiness of the building. The methodology behind the SRI is well defined in a relevant regulation of the Commission, and all assets are, let's say, scored, are ranked in accordance to 7 impact criteria, which are linked to the three pillars that we have referred to earlier. So with regard to the energy efficiency, we have the criteria of the energy efficiency percent, the maintenance, and the fall prediction. As far as the human comfort is concerned, we do have aspects related to comfort, convenience, health and well-being, as well as information to occupants. And with regard to the adaptability to smart grids, we have the energy flexibility and storage as another impact criterion. These are the 7 criteria based on which we evaluate the different assets of automation and control of a building, and we result to the final score of the SRI. Of course, these criteria assess the assets in 9 different domains, which are shown in this slide. So for heating, for cooling, for electric vehicles, for electricity, for the dynamic building envelope, for lighting, ventilation, and for monitoring and control. So these are the 9 domains which are mainly ranked in terms of the SRI, and under each domain we have those services that are categorized based on the 7 impact factors that we have shown in the slide before. And of course, at the end of the day, we have let's say the weighting of each of these criterion for the different domains, and the sum up of this procedure ends up to the final score for the SRI of a building. Now, in this slide, we demonstrate which member states have already proceeded in their testing stages for implementing the SRI. As you can see, France is ahead, is the first member state that has completed their test phase of the SRI, and they have defined their SRI catalog based on which they will proceed with their adaptation of the SRI. We have another 11 member states which are currently implementing their testing stages, including Spain, Denmark, Belgium, Finland, Cyprus, Croatia, and so forth. You can see them in this map. And we have other, let's say, followers, other member states which have still not initiated their testing stages. Now, what we see in this slide is how we calculate in practice the SRI. We see a tool, one of the tools that has been developed in a live project, the Smart Square project, is the Smart Ready Go tool. You can see the procedure of issuing an SRI. You see that we need to collect some general information related to the building, the type of the building, the location, the age of the building, the area, and so forth. And then we need to choose from the 9 different domains, which domains are present in the building that we evaluate. Doing that, we have the option either to assess with the method A or the method B. These are the 2 methods that we have for the SRI. The method A is a simplified method. The method B is for commercial buildings. And as you can see, this is an asset rating. The SRI is an asset rating. So for each service of the building, we choose a different, let's say, functionalities that we have. And each service is linked to a domain. And after doing that, we get the total score, which is given in a scale from 0 to 100 with the analysis for the 3 different pillars, as well as for the 7 impact factors, and then per domain and per service. So this gives you opportunity of conducting an SRI audit, and this is how it looks like. Now, just to conclude, some last remarks. These are the research trends in the SRI the past few years that has been in place. We retrieved this information from the SRI Observatory, another initiative of the Smart Square project. You can see that the Smart Readiness Indicator is mainly related to aspects such as energy, occupant, energy flexibility, energy savings, improvement, and so forth. And all, of course, is around the building sector. So these are more or less the trends in the field. And of course, we do expect to have a significant impact of the SRI on the design of building, given that this is a scoring scheme that will guide the market and the engineers and the designers towards choosing those solutions that will make our buildings smarter. Now, future trends, we do expect in the future to develop those, let's say, schemes that will enable the assessment of the buildings with real measurements, that is to have an operational SRI, which will also allow the integration of measurements, big data, as well as of machine learning methods. And of course, this will allow for a more occupant-centric design for our SRI. So we did introduce the Smart Readiness Indicator. We saw what are the main aspects of the indicator, how it was developed and delivered, what are the main, let's say, assessment criteria. We saw in practice how an SRI can be delivered. And of course, I'm at your disposal for any questions that you may have on the topic. Thank you.
Thank you very much, Paris. For the audience, we will have a Q&A session at the end of all the presentations. Now I leave the floor to Professor Joan Patterson from Cardiff University. Joan, the floor is yours.
Thank you. Could we possibly go to the first slide? 2 slides before, that's great, thank you. Hi everyone, so I'm Professor Jo Patterson from the Welsh School of Architecture at Cardiff University. I'm going to present some whole house energy system retrofits work that we've been doing in Wales, which has been funded through the Wales European Funding Office. And I will share the presentation with my colleague, Dr. Emmanuel Perisoglu. And we've been working together for the last 15 years, working on energy retrofits, particularly of social housing in Wales. So if we move to the next slide, please. I'd like to thank the Build Up team for inviting us to speak today, because it's a really good opportunity for us to share our very applied and practical work that we've been doing with on the Welsh housing stock. So next slide. Or is that? Thanks. So our housing stock across Europe is becoming old, very old, and we're also facing the challenge of a changing climate. We're also facing the challenge of the impact of the climate on the built environment, plus the need for us to maintain and operate our housing stock alongside the fact that we don't tend to do this kind of work anymore. We don't look after our houses as much as we do. In the past, we used to really have a lot of pride in care in kind of cleaning and doing DIY on our housing, but we don't tend to do that anymore. So we really need to kind of think about how we're going to transform our houses to be fit for future generations. So we like I said, we really need to transform our housing stock. The picture on the right is a house that was, or a pair of houses that were built in the 1920s. The car on the right hand side was built during the 1920s. So obviously the homes are quite still very desirable and still thought of being fit for purpose, whereas the car obviously isn't. So we really need to challenge the systems, the way that our houses are designed, so that they are really transformed to fit our future needs and our future requirements from the generation, which is very different compared to the time that the homes were actually built. Next slide. So the research that we've been carrying out in the Welsh School of Architecture has been under the headline Low Carbon Built Environment. And our work was really to help to reduce our dependency on fossil fuels, to obviously mitigate the impact of climate change at scale, to increase the use of low carbon energy sources, to reduce fuel poverty for the residents that are living in the homes, and also to provide a better quality built environment that is actually fit for the future. We've worked with a number of social housing companies, with a range of stakeholders, with residents, to really push forward this agenda in the Welsh housing stock. And we've carried out deep whole house retrofits on more than 40 homes across Wales. We've also built an energy positive house that's since been replicated within the social housing sector in Wales. And is being shown to perform both energy-wise and, as far as the residents are concerned, to a very high standard. Next slide. The approach that we've taken, we've always tried to select technologies, systems, energies and fabric changes that are affordable, because obviously we're very conscious of the social housing sector and housing people, owner occupiers, and the whole housing sector as a whole need to be able to afford to make the changes and find that attractive. So we've always tried to select solutions that are affordable. We've also tried to select solutions that are appropriate for the types of houses that they're being installed into. So not necessarily for the directly for the occupants living in the homes, but appropriate for the typology of homes. We've selected things that are replicable, so that and homes that are replicable, so that other people coming to visit the homes, because we've used them as demonstrators, have been able to come and kind of understand how they could repeat what we've done across a larger housing stock. Obviously, to reduce energy was critical, as well as to increase the comfort for the residents, and maintenance and operation for the social housing companies and the residents was also key in that decision-making process. We've tried to obviously reduce energy demand as the first option. So things through from loft and wall insulation right through to lighting and appliances. We've then combined that with renewable energy supply. In most cases, that's been PV panels. Usually where we could possibly do is integrate the PV panels into the roofs rather than using bolt-on panels to minimize the cost of roofing materials. So we didn't need to purchase tiles. And then we've combined that with energy storage as well to try and optimize the use of the renewable energy for the residents, and to use the energy as and when it's required. Slide. Throughout the process, we've very much used a methodological approach. So particularly with all of the retrofits, we've monitored the homes before and collected survey data using what we call a press tool to collect as much information as we can to inform the modelling. We've then modelled the properties to help the decision-making process. We've then gone on to demonstrate the technologies within the homes, and then we've continued to monitor them, which has been extremely valuable and provided really good evidence to support the decision-making process in other organisations, because we've really been able to demonstrate the change of energy performance, of occupant comfort, and many other factors for comparing pre and post retrofit. We've worked through the entire of the low carbon building energy system stages, and we feel that this has been really critical for the successful delivery of the projects. So this goes through from planning and data collection through to design, so making sure that the solutions that have been selected have been designed and carefully fitted into fit the type and the residents. Then we've made sure that the specifications identified at the design process are carried through into procurement, because often procurement is carried out by the financial team and they may not understand the technical requirements that are set out in the design stage. We've then engaged with stakeholders in the supply chain during the construction and installation phase, and then continue to engage with the housing owners, the occupants, and the supply chain to ensure that all of the technologies and solutions that have been installed operate as they should at the design stage, and that are also able to be maintained. So to give you an example of how we've actually done this in practice, we're going to present one of the case studies, which is a set of 6 bungalows that are built, that are located to the north of Swansea. They are very similar in type. They're owned by Swansea Council, who own about 13,000 social houses, and they were due for renovation. So working on these to kind of push the renovation into the whole house retrofit came at an ideal time for the council. Next slide. So the reason why they were up for renovation was that they were extremely inefficient in their energy performance. The heat losses were significant. So things like the white panels underneath the windows, there was huge heat losses. The lofts were leaky. They were just in very, very poor condition. The residents were facing very high heating costs, and they were already in poverty anyway. So this was really putting them into a really high, severe fuel poverty situation. The SAP ratings were between 12 and 17, so very, confirming and providing evidence on the poor performance. The homes were very drafty and uncomfortable for the residents, and there was also a lot of damp and mold. So not only kind of the cold was creating health issues, but there was potential for the damp and mold to enhance that as well. So lots of different, they were off gas. So the residents were either using LPG or oil or electric heating to heat their homes, which was very expensive. So a real need to go through this retrofit process to improve the homes for the residents. Now I'd like to hand over to Emmanuel Parasoglu, who will take us through the monitoring and data and evaluation process. Thank you.
Thank you, To. I hope that you can hear me. So one of the first challenges was to collect all the data possible in order to quantify the parameters, in order to be able to justify solutions, in order to be able to feed our modeling and simulation process, and also in order to be able to provide confidence in terms of future solutions and future scalability, and to quantify before retrofit and after retrofit performance of the systems and the whole house. So we ran a lot of fabric tests and we collected all the data available. We also installed a series of comfort and energy data so that we collect at least 1 year of data, so that we understand the consumption behavior, the profiles, and the comfort of the house. And these all fed into our simulation. So we calibrate our simulation tools and we ran several sensitivity simulations. And we provided to our collaborators, the owner of the house. We provided graphs like the one on the bottom right, an indication of the solutions we suggested and the impact on the investment cost, but also on the operational and the carbon emission, the operational energy and the carbon emission. So the final solution was a solution that was fabric first, but also would include energy generation, maximizing self-sufficiency, and also storage on site. There is a combination of external wall insulation, loft insulation, changes in the openings, and also a 2-slope PV and a battery together with some improvements in the air tightness and an MVHR unit that I'm going to analyze later on. One of the first challenges was to identify what would be a good performance, a good system, and how we evaluate, how we quantify. Because the engineers would insist that good performance is the cost-effective performance, or they would relate everything to energy reduction or cost benefits, or for some academics and engineers, operational carbon reduction, or how whole life carbon reduction would be the ultimate goal. However, when you deal with governments, local authorities, and also residents, social housing residents, there are the list of priorities is long, and in the end is a compromise between performance and other parameters, other risks. So one of the challenges was to identify what was a good system from the different perspectives of the stakeholders. So I'll bring you an example, an extreme example. The insurers were reluctant to insure innovation. So we wanted to make sure that whatever we applied was off the shelf, so that we give the insurers some confidence. So we started from fabric first. We improved the air tightness from about 8 to 4.5. We also changed some dummy panels, some plastic panels, and we increased the external wall insulation. We changed the openings, and the first active system, the first smart system, was a combination of a photovoltaic panel and a battery. And this system performed as a united system through this traffic control there, which is the gateway of the battery, a Tesla battery of 13.5 kilowatt hours, would charge and discharge at 5 kilowatts, and that would be able to accommodate the PV. The PV would run as self-sufficiency priority, so it will feed straight away the loads. If there is an excess, would charge the battery, and if there is an excess, will export to the grid. The battery, you can see the double arrows, could interact with the grid, charge or discharge, and can be also charged from the grid or the solar panel. We selected the ground source heat pump. All the parametric analysis we did in the initial stages was to use one borehole for the 6 bungalows, but in the end it was challenging, and our collaborator, the owner, prioritized individuality of energy source, and there were ownership issues as well. So we decided that we run one ground source heat pump for each of the houses. So the heat pump will be responsible for hot water and space heating, and it was controlled by a control panel, local control panel. And my colleague Clarice is going to explain more about the SRIs of these systems. The third system that can be considered as clever is a mechanical ventilation with heat recovery, and it's a system that provides preheated air, fresh air. It's a balanced system, so it supplies and extracts at the same rate, and it also has functionality to prevent overheating by a bypass of the heat exchanger. And again, a lot more will be described later on. In terms of performance, you can see on the left the average bungalow. So the blue ones are the ones that the residents pay for, whereas the orange one is what is provided by the battery and the PV, and the yellow one is what is consumed, and there is another export, the transparent one, and you can see from the energy balance that we have an energy positive average house. These 3 graphs here, so the annual operational energy breakdown, the annual operational carbon breakdown, and the cost based on 2022 prices. You can see the reduction. The first bar is just a benchmark from an average similar house in Wales and England. The second one is the pre-retrofit status, combining the fossil fuel and the electricity inputted, and you can see the reduction on the third bar. This is from a heating season for one of the houses, and you can see the significant comfort increase. So we managed in some of the cases to increase the comfort, especially the temperature, but also the relative humidity through the MVHR unit, and of course the CO2, the indoor CO2. This is an indication of an average of a 3.5 increase in temperature. Some few key outputs. We managed to reduce the energy import up to 87% for the ones that are aware of the EPC rating. The EPC rating rotated from 12 to 95. We also monitor the ground source heat pump because we were interested in the real life COP, and we monitored the stability, a great stability between 3.5 and 4. And we also calculated the embodied carbon and compare it to a new build. It was about 25% less. And there was significant improvements in indoor environment. And in terms of smart decisions, just to introduce to the next presentation, a lot of considerations were taken into account based on design, planning design, supply chain, but also considering owner's agenda, risks related to the controls and smartness, and also residents' engagement. Thank you. If you want to contact to the local mobile environment, you can contact to these emails, and I'll pass it to Anna.
Good afternoon, everyone, and thank you, BuildUP, for this opportunity to share our work, because it is very, very important to share knowledge. I'm Anna Badina, and I'm here together with my colleagues, Oleg Golubchikov and Clarice Blade de Souza, to talk about knowledge representation for comparing use cases in SRI application. I'll be doing this presentation together with Clarice. The work we are presenting is part of an EU project, chance project, which called SmartUP, Smartening the Modern Homes, Redesigning Power Dynamics for Domestic Space Digitalization. This is a social science project which examines the conception, production, and consumption of smart homes, adopting a human-centric approach and a system-of-system perspective, trying to understand what happens with the home when it becomes smart. We, as a UK team, we are part we concentrate on work package 3, which focuses on production from design to end use. Other partners concentrates on other work packages. One of our contribution to this project was the development of a knowledge representation system, which we call ONTA agency. Our ONTA agency maps SRI implementation in a structured way, compatible with BIM environments and ontologies related to smart building operations such as bricks and SRF. Our ONTA agency, therefore, is applicable to any smart building typology. Why did we create this ontology? Basically, to capture and compare the implementation of smart system in different contexts, using a standardized common structure, which could also help us make it more explicit, the agency behind it, and the emerging relationship of control, ownership, data sharing. Why do we need this? From a policy perspective, without tracing this relationship, we are not capable of assessing justice in smartization. From a technical perspective, without tracing this relationship, we are not capable of understanding the impact of our decisions on end users. Just bear in mind that design and operation, constrain, persuade, provide affordances and adaptive opportunities to end users. So smartization affects all of this. How do they map this to record, store, and retrieve best practice? This is particularly important when promoting the use of smart systems and energy transition, as we want more than user buy-in. We want transformative community engagement. So in what follows, we first provide a brief explanation of our knowledge representation system, and then demonstrate how it can be applied to the retrofit example presented earlier by Joe and Manas. On a methodological level, so we developed our ONTA agency through a merge between actor network theory and information science theory. And we developed the use case through reverse engineering the whole retrofit process described by Joe and Manas, using ONTA agency to map and record decisions in relation to the implementation of mechanical ventilation with heat recovery, heating, domestic hot water, electricity storage, electricity generation and storage services. And I will now pass it to Clarice, who will give you more details about this. Thank you.
Hi, everyone. Can you all hear me? Yeah. ONTA agency is basically, slides are not passing. Oh, ONTA agency is basically a relational agency-based ontology that maps information on who decides on the benefits and experiences delivered to different stakeholders involved in smart buildings. The building operation services providing these benefits and experiences up to the pieces of equipment delivering them, which you can see here. The functionality levels of smart ready services controlling these building operation services together with the agents behind them. We also talk about equipment ownership and data flows between different pieces of equipment and the stakeholders involved in a project. So how did we transform the case study into a use case? We examine and abstract what is transferable about it to other contexts without losing context information about the case itself. So we follow the steps indicated in this slide to build knowledge graphs using Onto Agency. And then we looked at priorities for design to extend asset life and increase asset value, as previously mentioned by Joe and Manus. We then listed the main design requirements, which you can see here, with responses associated to them. And then Manus and Joe already show you that these requirements and responses come from actually a combination of understanding building performance, residents, and city council needs. So we can see that these requirements and responses are then quite generic and transferable. But the data gathering, which you can see here, is quite context specific, as this is an experimental project. So we also abstracted key decision makers throughout the project delivery with the type of decisions undertaken at each stage, decisions that get constantly refined as the project progresses, as you can see on the diagram here. And here I just wanted to highlight a few things about this project which are quite context specific, like the client being a housing association means we have a socially engaged client, which might not be the case in other contexts. The residents are in this case long-term tenants, and this of course affects engagement, especially tenant engagement. The design team is also experimenting. This means opportunities to monitor and co-design, plus conversations to happen post-procurement, which is again unique to this context. So when we apply Onto Agency to assess provision, delivery, and control of mechanical ventilation with heat recovery, we can debrief the benefits and experiences into actually 6 abstract generic benefits and experiences, provide fresh air and preheat it via heat recovery, remove polluted air and boost this removal through, and then prevent overheating and save electricity. The benefits and experiences are provided by 3 building operation services according to the SRI taxonomy: balanced ventilation, boosted ventilation, and heat recovery via supply and exhaust fans and a heat exchanger. Balanced ventilation is here, in this case, controlled at SRI level 0 through a continuous supply. Boosted ventilation is controlled here at SRI level 3 by the MVHR control system, by humidistat sensors, and can be topped up on demand manually by the residents through a switcher, which is modeled as SRI level 0. Heat recovery is controlled by a thermostat at SRI level 1, which bypasses the heat exchanger when supply temperatures goes above 27 degrees. Now here we would like to highlight that when delivering this MVHR functionality, levels of smart services had to be sort of dismembered. So balanced ventilation is first. Continuously supply via this SRI level 0 to ensure compliance with building regulations and wiring regulations. 2, smartly controlled via this SRI level 3 to ensure moisture removal at an adequate rate to prevent mold growth. And also manually boosted with on-off switchers via SRI level 0 to ensure that users' control on increasing ventilation rates could, for instance, remove odor difficult to be sensed, remove vapor from cooking, etc. So dismembering controls in this case prevented the installation of an MVHR control panel and constrained residents' interaction with the MVHR system to a set of basic controls, so they cannot change delicate balances related to flow rate and temperatures, which were very carefully fine-tuned during commissioning. So this was a combination of design decision and client decision to get to this level or to do this dismembering. When we look at the heating and domestic hot water benefits and experiences related to thermal comfort with electricity saving and hot water provision with Legionella control were provided basically by services related to smart heating emission via smart radiators and smart heating generation with control of fluid temperatures and domestic hot water storage charging, all via a ground source heat pump with a control panel also reporting on heating performance. So the heating emission in this case is provided at SRI level 2 with thermostatic radiator valves connected to the ground source heat pump with an on-off heating generation and fluid distribution temperatures preset by installers, both at SRI level 0, controlled automatically by the ground source heat pump control system, which you can see here. The domestic hot water devices are fully automated with storage charging and setback thermostat plus Legionella control. And they run on automatic on-off with scheduled charging set again by installers during commissioning. So again, SRI level 1 here, to ensure compliance with health and safety regulations and also to make the ground source heat pump and the PVs to operate at full capacity together in the middle of the day, coordinating energy demand with generation to maximize self-sufficiency. There was no cost benefit associated with a higher level of smartness in this case to control the ground source heat pump, as the heating emission was just one circuit, thermostat dependent. So higher levels of smartness would only be cost effective if intelligent thermostats were installed, so that then the loads would be predicted to anticipate the demand. Now, when we look at the benefits and experiences for electricity savings provided by electricity optimization and storage, we can see that they are all related to electricity to the PV panel and inverter and the Tesla battery in terms of equipment delivering them. The optimization and storage were controlled by SRI functionality level 1, here with several reporting functions provided at higher SRI levels, basically 2 and 3. But residents actually relying on smart meter readings reporting information at SRI level 1 instead to make decisions related to energy use. The controls related to optimization and storage were capped at SRI level 1, despite the Tesla app being provided to residents and landlords to enable them to check electricity generation and storage, which could be effectively delivered at SRI level 3 and 4, but they were capped at level 1. Why was that? Because there were contractual issues with the utility company, which could not reward for energy exports when the customer is not the owner of the energy generation system, and when the owner of the energy generation system does not have a customer account with the utility company before purchase. So both of these prevented higher levels of smartness to actually be implemented despite capacity there to do so. It is also important for us to say here that the client was anyway reluctant to give tenants access to battery controls as they required knowledge to be used and can create risks related to extra maintenance and potential systems fault. So we also mapped ownership of equipment despite all of it belonging to the housing association, as you can see here. Just to highlight that this is an important relationship to map, particularly when housing owners are different than service owners. For example, in the case of energy sharing, which Manos mentioned, prevented like a single ground source heat pump to be installed for all the bungalows. And we finally mapped the data sharing here for the green arrows, in which we can see that the control panel for the ground source heat pump only shares data with the residents because it is not wireless and it's installed inside a property. The Tesla app, which is wireless, shares data with the residents and the client and Tesla company as part of contractual obligations. And the fact that it is wireless also exposes the system to interference, to outside interference, and enables data to be shared with the client and Tesla beyond residents only, which can open discussions about data protection and residents' rights. We can further discuss that into the question session if you want. Smart meters are, as expected, share information with the residents and the energy company for billing. And here we sort of try to conclude that and hope have shown that building operation services and the level of smartness associated to them are a complex product of expensive negotiations among stakeholders, and that happen throughout the project delivery. So they depend on multiple variables, as Manos showed in this nice diagram before, and multiple design requirements, many times not technical, and also on risks and liabilities associated to what is delivered, and also to how things are delivered. So the case of the insurance company that he cited before. For instance, we can see from this case that control functions might need to be dismembered to address certain types of regulations, constraints, while at the same time ensure requirements related to service provision and operation and maintenance are met, like we saw with the dismembering of the MVHR. Service provision might be enough if provided with lower levels of smartness because of building type and scale, like we saw with the case of the heating and domestic hot water, and that smartness might be capped by abilities to trade with the grid, like we saw with the PV panels. And these all need to be mapped because they give a completely different picture of reality without which we cannot document what is possible. So the idea is that the byproduct of mapping these relationships, we can then catalog use cases and create kind of libraries, transforming information into useful knowledge that can then be shared with regards to how realistic SRIs are shaped throughout the project delivery, which is something that is difficult to document and also makes the ideal not always becoming the real. The idea of creating an ontology is to make the process traceable and transparent, and it also enables information on potential solutions and best practice to be made easily accessible to design, operation, and policymaking teams. So I thank you for your attention and open the floor to questions, passing the baton to Arantxa.
Thank you so much, Clarice. Thank you so much to everybody. First, because you bring to us a lot of renovation that it's key right now. No, we need to improve our renovation rates. So let's go with some questions. Let's go with Paris. No, first one that presented. In one of your slides, you put the impact of SRI on the building design. That I think is key, and also perhaps it works also with the new Bauhaus, European Bauhaus initiative. Can we know a little bit more about the outcomes or your view of this, how SRI is impacting in the building design right now?
Yes, actually, what is very important to clarify is the fact that the SRI mainly addresses the building technical systems, not the building shell. There is an aspect related to the building shell, and that is a dynamic envelope, the dynamic shading of building openings, but it's mainly a system that addresses the building technical systems. To this end, when we discuss about building design, we mainly refer to the automation and control systems of the building that manage heating, cooling, lighting, domestic hot water, these aspects of the building. And to this end, the other important aspect in this field is that the SRI is an asset methodology in the sense that we define the performance, the smartness performance of the building based on the installed equipment. That means that we have the option to affect the SRI at the design stage of the building. So when we take our decisions on the technical systems to be installed, of course, when we have a major renovation, we can at that stage as well define the SRI, whereas we recognize that there are some limitations in the renovation stage for improving some of the technical systems of the building. Not all of them, but there are some limitations there. In any case, if our target, if one of the design criteria that we set at the initial stages of design of a building is to have as high smartness of the building as possible, then decisions are taken as well at the design stage, mainly what concerns the technical systems of the building, as well as some aspects such as natural lighting or even other aspects that may be directly related to the SRI. This is what was meant with the quote that the SRI will affect the design as well of buildings.
Awesome, Paris. Thank you so much. This relates directly, perhaps, with what Joan has presented us, right? With this traditional housing stock in Wales. That's how, and I know you have not talked too much about SRI, Joan, but how SRI relates to renovating traditional housing. As Paris was saying, it's a matter of technicity. Sometimes we don't have the space. No, we have the problem of these narrow, for example, facades and narrow structures in fact, in UK. How you are dealing with that, and what have you seen during the process of effectively renovating this traditional housing? You are muted, I think, Joan.
Put my
yeah, now,
yeah,
perfect.
there you go. Yeah, sorry. So I think one of the biggest challenges of all around all of this is about data collection and then communication and collaboration. And I think that all of those, the Smart Readiness Indicator, all the kind of monitoring, integration with the grid, all of these things need to be embedded in that entire process, right through from planning to design, procurement, etc. Because if it isn't, then nothing gets used as it should, as it should do in practice. We can collect as much data as we want to collect. We can monitor as much as we want, but if people don't understand what they're collecting and monitoring throughout that process, and then interpreting that data in a way that's really useful to make changes and make corrections, then we're kind of wasting our time. So we need to really make sure that the real value of anything that's being collected and all of this work is great. All the monitoring work, everything is really good because it's gathering that evidence, but we need to make sure that we're using the evidence as effectively as we possibly can.
Absolutely. And the numbers that you show, both of you, Emanuela and yourself, were outstanding, right? How replicable are these strategies with the same level of success in other typologies or countries? Because I think also Clarice referred to project specifics, right? Very interesting for all of us working in this area as we want to reach more impact. How much replicable, or how replicable are these strategies that you have implemented here?
So we've implemented the strategies across, well, more than 40 homes, and the savings and the impact, the positive benefits are kind of all, I mean, they depend obviously in the depth and the type of heating system that's been implemented, but generally the benefits are, they're seen across every one of those projects. So the residents are better off, the built environment has been improved, carbon emissions have reduced significantly. So for every single project that we've worked on, those benefits are transferable to all stock, but it's about that care and delivery that throughout the entire process, which is fundamental. I'll hand over to Manos, sorry.
Yeah.
I just wanted to point out, continue with what Joe said, is that it has to do with what you prioritize, what we prioritize as designers, as service engineers, but most importantly as governments, housing authorities. Because if it's all about cost effectiveness, is it all about payback? If we don't consider operational energy, operational carbon, corporate impact on the NHS, which is the health system in the UK. So if we don't prioritize other performance indicators that are equally important, and we only consider capital cost, and then it's very hard for some of the systems to be efficient. It's not only though about payback. However, some of the systems are cost effective. It could be an air source heat pump rather than a ground source heat pump. It could be a slightly smaller battery. But this was a demo product indicating the cost benefits, but also the comfort, carbon, and other benefits.
I really think that this is one of the biggest strengths of your project, to be so realistic and to make a direct link to the user with what Clarissa and Anna presented. And here we can set what is the limit to smartness from a user perspective.
Can I take this one?
Sure, it's for you.
I think the idea of mapping Manos and Joe's project is exactly to explore that aspect, to what is the limit to smartness, and that will be context-based, and it depends on multiple factors, not only on the engagement with the residents, but also on how much the client wants to provide these controls, and that is also dependent on other factors which are risks for the client, such as insurance risks, maintenance risks, and also fine tunings that were achieved, like in this project specifically related to the MVHR, that were achieved during commissioning and also during end use. So it's all a very delicate balance, which is very difficult to predict in the design stage, because things do develop as you go along with the construction and the installation and so on. So the real in the end is never exactly as designed, because these decisions are accommodated throughout the process. And that accommodation includes also controls. And I think we had lots of conversations with Joe and Manos. And one interesting feature was exactly, but can we lock some parts of this control panel so that the user cannot interfere with that, but then we can, and so on. So there were lots of other discussions happening in relation to how much control is adequate in different contexts. And we believe that for a realistic adoption of the SRIs, we need to be aware of those, because that is really like when we are grounded to reality and we're with projects that we can see what's happening. Not sure I answered your question, but the limits are.
You did.
Yeah.
And to finish, because we are already a few minutes past, but it's okay. Very interesting topic. So you talk about knowledge management. You talk yourself, but I think it's extensive for all of you. What about knowledge sharing? It's equal knowledge management to knowledge sharing. Are you looking forward to create a hub or a place where these outcomes that are so sometimes specific, but also sometimes something that you can really benefit for other projects, but also for reality, right? What are you gonna do with all the outcomes, all the information that is coming out of the project itself and from your research?
From our perspective, we have the ontology already shared in Zenodo, and I can potentially give you the link to it, Orange, so you can publish in BuildUp. And for Manos and Joe, I guess they are documenting, so I'll pass them how they are documenting.
So we've established the Centre for a Low Carbon Built Environment at the Welsh School of Architecture, and we've been working very closely with Welsh Government to kind of demonstrate the evidence that we've got coming through our projects. So we've created a set of fact sheets that summarize all of the case studies that we've worked on over the past. We've used the language and the way of presenting that so that it's really accessible to a wide range of stakeholders. And the projects have helped to help to support the delivery of the optimized retrofit program, which is a large-scale funding package of over £200 million in Wales to kind of really push forward the retrofit agenda. So we'd like to just share our outcomes really widely as case studies to really demonstrate what can be delivered as a result of taking a contextual approach, but also a kind of process and evidence-based approach to really create housing stock that is fit for the future.
What concerns our work, that is the one that was presented at the first, let's say, presentation. Part of this work has been delivered in the Smart Square project, which is a live-set project funded by the European Commission, which is ongoing currently until 25. We have, besides the webpage of the project, we have at least two, let's say, hubs, which we aim to maintain after completion of the project. The first one is the SRI Observatory, from which we have demonstrated the tracker for the adaptation of the SRI among member states, as well as the science tracker, which shows what are the trends. There is also an annual outlook of the SRI in this observatory. So it's sriobservatory.eu, let's say the hub for that one. And of course, we also have launched a tool which is open and accessible to everyone. That is Smart Ready Go. It's the tool that we use to demonstrate how the SRI actually performs. This one is also an open tool accessible to everyone. Let's say link to that one, it's smart-ready-go.eu. So part of the work that we carry out for SRI can be retrieved from these sources.
Outstanding. For you to know, I have put all your links for the audience. Hope they have time to check them. So Paris, Emmanuel, Joanne, Clarice, Anna, Oleg, thank you so much. Thank you for this interest and for taking the time to let us know what is going on and what you're working in, and give us a glimpse. I know you have time to complete, so we will follow you from Build Up, that's for sure. Thank you also to the audience for attending to the webinar. A reminder that you will be able to find the recording of today's webinar on the Build Up portal, hopefully tomorrow, and our YouTube channel in the coming days. Build Up will be back with more webinars in the pipeline after the holiday break in September. So keep an eye on the Build Up calendar of events and our social media for updates on this. Be also sure to register on the Build Up website to be able to share and disseminate your own content, and follow us on social media for updates. We wish you all a very pleasant summertime. Thank you and goodbye. Thank you, everybody. Bye-bye.
Thank you.
Thank you.